College Engineering Seminar Series. And today we have Dr. John Thawing, who's going to talk about liquefaction. We're very excited about it. Well,
thanks. Yeah, all right. Yeah. No, so I have an alternate title as well, liquefaction susceptibility of soon to be thawed soil, formerly known as permafrost, right? So just a little longer title there. A little bit about what we'll be covering today. So essentially, just a little bit of background on liquefaction, just so we're all kind of on the same page. Believe it or not, Anchorage used to have permafrost, and we have a liquefaction problem. So that's kind of a nice analog for the rest of the state, and permafrost across there. So we'll talk a little bit about Anchorage, some methods for characterizing liquefaction. All right, and then a little bit on permafrost and a few case histories. Try to keep it interesting. And at the end of the day, this isn't necessarily a presentation with a bunch of solutions, but a bunch of things to kind of take away and think about, because there are some challenges ahead of us. Next slide. Sure, next slide. All right, so introduction to liquefaction. I don't know, everybody know what liquefaction is? All right, so it's essentially a strength loss due to ground shaking. Effective stresses go down and loss of strength. And typically you have loose saturated sandy soil and an earthquake, and oftentimes this happens in more younger alluvial soils that haven't been consolidated as much or densified, right? So this kind of loose state that you're sitting in, and so. Looking just kind of at, void ratio plot, you have your loose soils above your critical void ratio line and dense soils below. I don't have a lot of plots here, but we got a few of them. So bear with me. There's no quiz at the end. Here we are.
we can make a quiz.
We can make a quiz. All right. So consequences of liquefaction. Here are a few examples of liquefaction. Some more recent than others. Both the earthquake in the upper right-hand corner. Pretty significant settlement due to liquefaction. You got the Nevada earthquake and a couple others. But really, at the end of the day, we know liquefaction can be bad. We know that we need to design against it. So what is it that we're actually doing? So there's the cyclic stress ratio, CSR. We have no control over, right? That's Mother Earth. That's the loading that Mother Earth puts into us. The other, the cyclic resistance ratio is actually the one we kind of have control over, or we can measure, right? And that one is the one where we're looking at the density of the soil. How dense is the soil? Is it loose, like we said, you need to have, or is it dense? And if it is loose, how dense do we need to make it so that it doesn't liquefy an earthquake, right? That's the engineering piece of this. And so there's this little sick, nasty equation here for using this N160 value. N160 is that is a corrected blow count, right? So when you go out into the field, and everybody familiar with doing borings and anybody, Chris, you know that? Yeah. So you go out there, you go back in the old days, they used to have a cat head rope system, and you raise and drop the hammer and drive that sampler, and then somebody with enough fingers counts how many blows that was per 6 inches. You add them up and you get blows per foot, right? So we've got a lot of different relationships we've built over time based on that blows per foot. Now, one thing that's important to know is that when you're out in the field and you have a field set of blow counts, that's a good starting point, but it doesn't correct for a lot of different things. Joe with this hammer or John with that hammer may have kind of different approaches to driving that sampler, and so we've got to correct for the energy of the sampler. We got to correct for the depth of the sampler. We got to correct for the diameter of the borehole. There's a whole bunch of correction factors that we have to do. And so you see this N160 This is basically a corrected value for 60% energy efficiency on the hammer, and then one atmosphere of pressure for the surface. So we go through this whole equation here in order to then correct these blow counts. So the blow counts we're doing in Japan versus the blow counts we're doing here in Alaska versus everywhere else, they're all basically the same. And so you're looking from one log to another. N160 to N160, you should have kind of a good sense for what's going on. And then you'll notice in this CRR equation, there's also this CS subscript. So there's an additional modifier that they've applied for clean sand, right, to account for the fines content of the soil. So there's all kinds of things that you got to do in order to get to this, beloved N160 value. And if you read any good geotech report, it says, beware, the blow counts in your boring logs are field uncorrected blow counts. And so what they're saying is we haven't done this to your blows, right? So that's the first thing to understand. And what you're really trying to do is you're trying to understand how dense is this soil? Is it loose or is it dense, right? That's at the end of the day, that's what all of these equations really attempt to answer. So we then calculate a factor of safety. Geotech still love AFD design, essentially factor of safety design. And so we look at the ratio of the cyclic resistance to the cyclic shear stress, and is it above 1 or not? And if it's above 1, then we think we're kind of better placed than if it's below 1, right? Below 1 is bad. All right, so again, back to kind of the old cat head rope system. All this happens now with an auto hammer. You don't see all the magic happening, but yeah, you get to back in the day, we'd have to watch the driller make sure they only had 2 wraps around the cat head. They try to do 3, it's a lot less work, but it changes your blow count, right? And all kinds of factors really impact the quality of your blow count. We also have cone penetration testing. I don't know how many are familiar with cone penetration testing. It's not that common here in Alaska. There are a couple rigs available that push cone, but we have some pretty challenging soils, often a lot of cobbles and different things that make it difficult to actually push cone. But so up here in Alaska, we typically rely on the standard penetration test, so that's kind of where all the magic happens for characterization. All right, then there are other ways that we can also characterize the density of the soil. One would be shear wave velocity measurements. So you could do a downhole shear wave velocity profile. Like ASC 7 leans pretty heavily on shear wave velocities in the upper 100 feet to characterize your soil. There's a number of methods out there to take shear wave velocity and estimate the liquefaction potential based on that. They're not that common, and I haven't found them to be that reliable when you compare them to SPT. But SPT is also not very reliable either. So it's kind of a shot in the dark. And then surface testing, MASW, so multi-channel analysis of surface waves, is a geophysical method that you can actually run an array of geophones out and collect a shear wave velocity profile of your site as well, without having to drill any holes. And I think, to be honest with you, as ASC 722 and others move forward with the new emphasis on shear wave velocity measurements, you're going to see a lot more MASW testing for sites, because it's pretty cheap and it gives you some pretty good data. But also that shear wave velocity measurement will help you estimate whether you might have soils that are liquefiable. And then other methods, this one here is basically looking at geologic mapping and saying, all right, do I have young alluvial deposits, or do I have something else, right? Because you can use those analogs to compare. Now, this map here is of the Fairbanks area, and you notice all the light yellow. All the light yellow, if you use that analog, you'd say all of this is liquefiable. All right. Is it terribly useful? Maybe not. But it gives you another tool without again having to drill a hole. So other methods for estimating whether you've got liquefaction. All right. So here's a couple photos. There's a whole plethora of photos from the 2018 earthquake, you know, we had liquefaction here in Anchorage. And again, the only reason I really bring this up is because Anchorage had permafrost. If you look at the 1980 atlas of Alaska or of Anchorage, there's actually a map on there that shows extensive potential permafrost. All right, this is 1980, not that long ago. But you know, permafrost was here, and now we tend to not worry about it. But you can take that and use it as an analog for places like Fairbanks or other places that have discontinuous permafrost like we did have. Sorry. At the moment, yep, at the moment. So, you know, this is just a shot of you know, some of the calculations that are involved in figuring out whether or not you might have liquefaction hazard. And so this is actually from a site here in Anchorage where we observed liquefaction during the 2018 earthquake, and so then we subsequently drilled it. And so using the inputs from our magnitude 7.1 earthquake and the PGA that was measured at that site, because the site is actually instrumented, we can then estimate whether or not we have liquefaction, and lo and behold, the method works, right? So we knew the answer already, and the method works to give you that same result. So that's really good. All right, now we're going to shift gears just a little bit to permafrost. I think most of us may be familiar with permafrost. It's that frozen ground that stays frozen for at least 2 years, kind of an odd definition, but you got to start somewhere. But what we're talking about is permafrost that's been frozen for a good long time. And you have an active layer, all right? This is that seasonally frozen ground. So here in Anchorage, we get seasonally frozen ground, you know, down to about 12 feet or so, plus or minus. Fairbanks is a little deeper. And so, but if your permafrost is within that, you know, say 12. We'll pump the brakes, huh?
There we go. All right, now, yes.
Well, I have 150 slides to get through.
No, I'm just kidding. You're good.
I'm just kidding.
All right, go ahead.
Thank you for interrupting your train.
All right. Yeah, no, that's all right. That's all right. I don't have a train of thought, so you can't interrupt.
Or making a card.
Yeah, right.
All right, perfect.
We good?
Yep.
All right, for now. All right, so you know, permafrost is something that we as engineers, scientists, you know, deal with pretty regularly. But what I'm going to talk about more specifically are these kind of peach zones, these talics, and you can have closed talics, you can have an open talic, and then you know, through talic that never actually ever have permafrost below it. But the ones that are going to be the most problematic are those ones that, you know, as by the definition, are below your seasonally frozen ground, right? But above your permafrost table, right? So you now have this zone where your seasonally frozen ground never freezes back to top of permafrost, right? So you'll have this zone of thawed soil. And that's the problem that we're going to kind of talk about, because as we see permafrost degrading over time, we're going to have more and more of that talic development, and even a thin layer of that talic development will cause us problems on the engineering side from a liquefaction standpoint. If there are questions, I can see questions maybe brewing. Feel free to
It's just an act.
I'm sorry.
I'm just doing an act.
Okay,
I
I like
like
it.
focus.
focused, all right.
It's not, don't worry about it. I'm keeping up with you there.
Yeah, so, and I love this figure by, Vladimir Romanovsky of UAF. And so I steal it and use it regularly because, one of the underlying, premises here for this whole presentation is that we have permafrost degradation, right? And so I'm not gonna go into a lot of, the details behind this, but I do want you to observe that this is, 20 meters, 60 feet below ground surface. These are measurements starting from the 70s to now, and all we see is this massive trend towards thawing ground. And this is across the state. Now, interestingly enough, as you move south, it gets to be kind of less and less, but that has to do with phase change more than it does temperature, right? And so, this will be a problem unless you're retiring tomorrow. This will be a problem for you as an engineer in your career. Now, just kind of putting that together again, we have this zone of discontinuous permafrost in Alaska. Discontinuous permafrost is basically permafrost that's not fully connected, not deep. You've got talc development. You've got it's fairly warm. Whereas continuous permafrost is you have a minor talc here or there, but you don't have much disruption, right? And then on the right-hand side is the seismic hazard map. This is borrowed from the USGS is the most recent hazard mapping of Alaska from the 2023 model. You can see that we have seismic hazard, right? And so the combination, of earthquakes and degraded permafrost again kind of ties back to the need for this conversation today. All right, so there's this liquefaction susceptibility. I think it really, I really love this chart here. And this chart essentially shows Farmers Loop and the monitoring that has been done at Farmers Loop up in Fairbanks. And this area was basically kept vegetated as is. This area has been cleared of major vegetation, but the minor vegetation is still there. And this area essentially has been cleared of all vegetation, right? So what you're looking at is with time, what the degradation of the permafrost has been. And what I find pretty shocking is that 61 years after this area was cleared, we essentially have 31 feet of degradation so we're not talking about a thin talc here. We're talking about a pretty major talc. And you can think of it as when I put a road, I put a building pad, I put whatever I'm putting on top of this. This is what's happening at my site that back in the day I thought I had permafrost, right? Unless you've done modifications to try to maintain that permafrost, right? This is the kind of thing that's happening under our roads and why we're seeing, shoulder failures and different things because of this degradation here. And so it's a great deal. Now you can think about if you had a site here that you were working on today, and you drill down and you find permafrost at 4 feet down, or 3.5 feet down. This is today. Well, what's going to happen to it in the future, right? And so this kind of gives you a sense for what one of the possibilities is for the behavior at your site. And so then you think, if you have say a 50-year design life for a structure, what impacts are you going to anticipate from the development of that structure to the permafrost below? And then are you accounting for that? And then how you measure it today, because today it's like this, it's frozen, right? And so blow counts in frozen ground are pretty meaningless, right? You count them because you don't have any fingers and toes left. You run out of them because the blow count's really high. But at the end of the day, you discard the blow counts because you have a stiff material, it's frozen. But you take the sample, right? And the whole goal of driving that sampler was to take the sample back. So there's a number of, kind of issues, that relate, with this. And so we'll look at, so my dear friend, Dr. Zhang or Yang, here at the university gave me a few slides, based on, and again, this kind of shows this, unfrozen, this talic layer. So you got your active layer, your talic layer, and then, your permafrost below. But more to the point, the 2002, magnitude 7.9 Denali earthquake. And some of the work that, he and some of his students have worked on, here on this. And so one of the things that they found, was some lateral spreading, and liquefaction, due to roadway construction over permafrost. And so this was some damage that was measured and evaluated after that earthquake. But the one that I want to focus a little bit more on is this Northway Airport, because I think this is a nice kind of analogy for what we're talking about today. So back in the day, in World War II times, the Northway Airport was built. And it was built on permafrost that was very near the surface. And so we have some observations of the permafrost degradation over time. Okay. And so you can see from 1951 to 1973, in the paved area, the degradation wasn't as significant as it was on the shoulders and the gravel areas. And we think that that's primarily due to the fact that they cleared this runway. And so it allowed a lot more cold air to penetrate into the ground and maintain that permafrost. However, all that snow that they cleared off of the runway, they put on the shoulders. And snow is a great insulator, right? And so we didn't allow as much cold to get into the ground. And so it's pretty interesting when you plot the Linnell plots. So if I went back and just held this, we fondly term this the Linnell plot. Just so that we're all on the same page there. But when you plot the Linnell plot on here, this gravel plots really nicely in that. And so you can see that we have this permafrost table and a pretty significant degradation of that permafrost. And it matches really well with Farmers Loop Road as well, too. So looking at some blow counts here, this was some data that was taken back in the day with at a time where permafrost had degraded roughly down to 15 feet or so, and we end up with this liquefiable layer, and so you actually have a layer that captures itself as potentially liquefiable. We can go back and we can measure it now because it's thawed, right? And the blow counts actually matter. And there's the result, right? So we had liquefaction damage. We had some spreading. I don't know if I'd be as brave as that guy to climb in that crack there, because you just never know what an aftershock's going to do for you. But that's what Northway looked like after the 7.9 earthquake. Now, if it had been frozen, and permafrost had been maintained, throughout the depth, this would not have been the damage mode that you would see here if there was damage at all. So that gives us a case for being concerned. So kind of back to our poor guy pulling on the cat and rope system. In frozen ground, we typically assume that we don't have a liquefaction hazard. And that's due to the fact that our pore pressure is locked up, it's frozen, right? But with, we'll still collect our SPT samples, but we do that because we're trying to get samples out of the ground. And then conventional CPT, the Russians push a lot of CPT. We don't push very much CPT, but they do it about 10 times slower than what we advance CPT in the thaw ground. And they can do a lot of things. They learn a lot about permafrost by doing that. But one thing they don't learn is whether it's liquefiable or not, right? And so CPT is not terribly useful for frozen ground to estimate liquefaction potential in the future, right? And so that's kind of the big question here. All right, so we're going to talk about another case history. Case history near Fairbanks, and this is not one where we've evaluated or where we've seen liquefaction, but it's one that we considered whether we have liquefaction or not. So we have this nice figure here, and we have this area that's been cleared since for a long time, and then we have this area that's treed. And then basically, what we found when we did our geotechnical exploration is we had a Linnell plot right here at this site where we had deep seasonal or deep thaw in the area that had been developed, and then permafrost was basically 5 feet below grade in the trees, right? And you have that, like, I mean, as distinct as you can imagine, you're drilling, in the open area, and you find no permafrost down to 100 feet, and then you go into the trees, and it's right there at 5 feet. I mean, it's that drastic with the tree line. And so we found that we drilled several hundred borings for projects over this area, and we found essentially the same thing. In the trees, it was frozen, and out of the trees, it wasn't. Like we said before, we're an earthquake country. There's been nearly 10 magnitude 7+ earthquakes in the last 30+ years. So we know that we got the potential for pretty significant earthquake activity up there. So what I was trying to do, and this was a post project evaluation, right? This was something I basically kind of did on nights and weekends. I said, how can I use the data that I have to evaluate whether or not I could tell in the frozen soil whether or not I was going to have a liquefaction problem. All right, and so what I did was I plotted up the thawed soils and calculated N160, and basically we had a liquefaction problem in the thawed ground, but we didn't have a liquefaction problem in the frozen ground because it's frozen, right? But in 50 years from now, after they've developed it, what might that tell us from the thawed site? So this is just a basic plot of the average flow counts, and you can see that it kind of hovers around that 32 blows per foot until it gets deeper, and then you had some really loose soil and some denser soil. Now, so when I'll take a look at just one boring here, and this boring 66, it has this zone of really loose low blow counts, and basically we have a factor of safety less than 1 in this 20 to 40 foot range, right? And so this is just one example of the many thawed soils. And so I did some math, right? Basically opened up the old geotech engineering 101, deal, and looked at relationships to calculate the void ratio and the degree of saturation. Essentially, void ratio is a measure of relative density, right? It tells you how dense or how loose something is. And then I wanted to understand the degree of saturation. And so this was just basically to try to average things out. I should note that this was a paper that some of my colleagues and I put together for the ASCE 2017 Cold Regions Engineering Conference in Duluth. So you can find that on the ASCE deal. I don't necessarily confirm nor deny that this method works, right? But it is a method that I use that seemed to work pretty well. And so one of the things that we know is that frozen samples tend to have less saturation than 100%. But when you're below groundwater, after your site's thawed, and you have full saturation, you could assume that you're going to get nearly 100% saturation, right? And so you're pretty wet there. Then I promise there are not very many more equations, then we estimate the relative density, and you can do that with this little guy here. And then, from that, we estimate the N160 because I figure out my relative density. I can use an empirical equation to back into the N160 value, right? So this is basically just a bunch of math trying to get some relative density information to N160 blow count so that I can then do a liquefaction analysis, right? All right, so if we have this boring here, this is BH70. And you can see that the blow counts are really high in the frozen case. Now, if I apply all that math back in the day, I can correct that frozen case to a thawed case. And what I find is that I actually have really loose soil that has a lot of ice, right? And so when I'm looking at the soil, it's sands and gravels, right? But when I'm in the thawed side, I see these sands and gravels and they're really wet. I don't know how wet because I lose some water out of the bottom with the sampler. But when I sample over in the frozen area, I get all the water and all the soil. And you can see that you got some ice, right? Now ice is filling up space, right? That the soil could be because it's in a fairly loose state. Let's see, so then when I do that with all of the information I've got for all of my sites, then I can plot this up again. And so I call this my average frozen corrected, and basically I have these zones of potentially liquefiable soil or lower blow count material, and sometimes it gets a little denser, and sometimes it's looser. So what it really comes down to for this method is I'm really putting a lot of weight on moisture content, right? And I'm saying if I've got a bunch of ice in the sands and gravels, then I've got a sample that's in a really loose state, right? And so I can plot up this nice N160 blow count to moisture content. You know, basically the more ice I've got, the lower blow counts I've got. They're pretty simple, right? A lot of ice, low blow counts. And it seems to work out. And I have a nice analog next door with a thawed site. And so you can do this with a whole bunch of different levels of saturation of the frozen sample, and get basically a wide variety or a family of curves for blow counts. Then all you have to do is measure your saturation of your frozen sample, and you say, all right, this is what a corrected N160 blow count would be. All right, and then this is kind of the steps through the whole thing, and you know, we don't need to belabor that point. All right, there are some limitations to this method, right? So this was like one site, a whole bunch of borings in the Tanana River Basin for one site, and you know, I made quite a few assumptions and ran a bunch of math, right? And so it seemed to work out. It passes the sniff test as far as you know, ice content and assumed density, but that's, you know, again, you know, something that needs to be evaluated a little further. So, you know, what can we do? This is you know, this is the Kivalina Bridge, and this was happening at the same time I was doing that other study. And the Kivalina Bridge, basically we had highly saline soils where we had the low freezing point or a lower freezing point, and we were basically looking at what was going to happen, you know, from a climate change perspective for the next 75 years for this bridge, right? So this is a bridge. We're expecting it's you know, it takes folks to the school up the hill, and eventually the future community that they're looking at. But the DOT was concerned, you know, they're going to get 75 years out of this bridge, right? And so we looked at the piles, we looked at the soil, and we did a bunch of analyses based on what we thought the behavior of those soils were going to be once they thawed, or once we lost our permafrost. And so what we found was that you have a significant change in the surface resistance for the piles. You have lateral resistance changes, right, as your layers soften. You also have liquefaction and then potentially down drag that causes all this pile interaction and challenges of the pile. So the answer for this job was drive the piles a lot deeper, right? And so that was you know, and basically, you know, throw money at the problem, right? And that's what we did for this one. And that was, you know, I think I'll be honest, it's fairly forward thinking of the DOT, right? Because you got this bridge kind of out in the middle of nowhere, and you know, they still, you know, kept the focus, you know, that they wanted 75 years out of this thing, and they were willing to put the money into making sure that it was there in 75 years. So that, you know, that was a good thing. But you know, this is I wouldn't say crystal ballish, but there's no direction, in the code or, methodologies for, geotechnical engineers on how to just, understand what this is gonna look like in 75 years, right? And so, and this is kind of, one of the, I would say, this is the impetus for this presentation is to at least acknowledge that we have, this is an issue. All right, and then, I wouldn't be doing anybody any favors if I didn't bring up the critical state approach. I don't know, critical state soil mechanics folks out there? Nobody, all right? They don't teach this in school, and this is a tragedy, but, critical state soil mechanics, basically describes liquefaction really well. And again, we saw a plot similar to this where we have loose soils on this side, dense soils on this side. And we can understand what happens over the life of soil by plotting it up here. And I'll just quickly go through this because I presented this at UCOP or the European Conference on Permafrost last year, yeah, 2023. This is kind of an interesting deal, but basically. We'll step through it, A to B. So A is your originally frozen ground, and then over time it thaws, right? And as it thaws, we can estimate the consolidation, right? That we see up on the north slope, as permafrost is not thawing, but is warming. We're getting this consolidation, right? We're getting ground surface changes, and so that's your A to B, right? And then as we move from a thaw consolidation, we basically move from B to C. Now C to D is that liquefaction piece where we lose vertical effective stress, but it doesn't change its void ratio. And this is kind of a combination of a number of different research focuses, but basically this is a model or a methodology for estimating permafrost response as it thaws, again, related to void ratio. So I don't expect this one taking off that soon, but again, the critical state approach, this is the part that makes me chuckle is critical state soil mechanics for liquefaction analysis. They pay a lot of money to freeze soil to then sample it so they can get good samples to take into the lab. Now, what we have is we've already got that frozen soil. Nobody has to invest a penny into to freezing the soil because it's already frozen, right? So we're already a step ahead. So I'm really excited about research really heading into this direction and helping us out here because we've already done the hard work and we've got frozen soil. And so then you can do a bunch of laboratory tests to evaluate all those things that I've been talking about. So the concluding remarks, the first step is, to admit that you have a problem. And I think that's, kind of the big issue here is that, we do have a, permafrost degradation problem. It's an exciting problem, I would argue, because, there's not a lot of real guidance there, right? So we as a community have to figure out the direction that we want to go. Both the current and future infrastructure will be challenged by this, right? Current infrastructure is potentially causing more thaw in areas, especially if it hasn't been designed properly. And then, as that loose saturated soil becomes thawed, it's much more susceptible to liquefaction. But again, characterizing that, right? How do you go out to the field today and go measure, the permafrost in its current state and tell me whether it's liquefiable or not in the future? And so we have some analogs for that, but it's a really challenging topic. It's a bigger issue than just building a foundation or building a building, right? Because your building or your structure is connected to utilities, and your utilities are connected to something. And so you may be able to improve the ground for just your building, but if your sewer, your gravity sewer, shifts because of liquefaction, then your building is no longer serviced by that utility, right? And so this is not just within the envelope of a single piece of infrastructure. And then, if your embankment fails in front of the bridge, we just go out and build it, right? But scarce resources, may not allow that, right? And then worse yet, what if the bridge fails, right? It takes a little bit longer to rebuild that bridge, right? So, yeah, again, the presentation is intended to, as food for thought. There's still a lot of work to be done, in this arena. And it'll be, really an interesting, kind of area to focus on. And the challenges to us, I gave you the example of a Kivalina Bridge and driving piles. It may not be as simple as just driving the piles deeper, right? This was another project, not Kivalina, where we had challenges driving piles into permafrost. And this permafrost was like 31-degree permafrost, so it wasn't that frozen. And that's what it looks like. So just, go ahead and drive a little deeper. And so then how will these changes, affect design life, right? You anticipate a 50-year design life, you anticipate a 75-year design life. But is that a reasonable design life anymore in an area where the properties of the soil are changing from year to year to year? And then, can we properly characterize that? And, how are we going to, devise new methods to evaluate whether or not we have a liquefaction hazard or any other hazard? And then it all comes down to dollars, right? And, how do we account for that? So with that, thank you very much. I think I'm up. Yeah, spot on. All right. All right.
Great, question? So two questions. One's stupid. How do you measure the void ratio? The amount you melt off the water and just do it by solid.
So-
volume versus.
Yeah, basically, it's a volume relationship. So basically, so for the current void state, I assume a specific gravity or measure a specific gravity. I've got my unit weight of the water and I've got my unit weight of soil. So the easy one is to actually measure the in situ or the current void ratio. The harder one is to measure E min and D max. If you typically need to have a larger sample and then run a number of tests to understand where the E min and D max are. But understanding where you are, at least, within that continuum is a lot easier. So it's one you can direct.
And then have you seen, is there actually any good data or models or predictions on where and how much the permafrost is going to obviously it's related to the actual global temperatures changes model. But
Yeah, I mean, there are some models out there, right, that have tried to make this wag. And it's kind of goes back to the old adage, right? All models are wrong, but some are useful. And so it's hard to say. Yeah, I mean, as a community, if you were to query all of us, I think you'd get more answers than the number of people in here on where we're going. So that's really a hard question to answer.
I have more of a comment. I did my thesis on the Corral site on Farmer's Loop there.
Okay.
We were doing our drilling for that site, the top like 20 feet of that where we were at, where our piles was like thawed. And when we drove our split spoon down in there, you can basically just see the thawed ice lenses in that silt. They're still there. So it's just like extremely young, super unconsolidated deposit.
Yeah.
Liquefied for sure. And then ice content below. So it's, I think, over 100% in some places. So it's pretty high. So
Yeah.
this is kind of an interesting method. You could actually estimate the liquefaction of that permafrost flow. It's pretty neat.
Yeah, I mean, we'll see. I guess time will tell.
What do you assume the consolidation of those ice lenses is going to be? Like if you take a water sample, or ice sample of that permafrost, like how are you deciding how much it's going to consolidate?
So we do a test in our lab called basically a thaw strain test.
Mhm.
And what we see basically is you know, those ice lenses go away 100%, right? So you lose all of that for sure. If you have you know, ice over a certain stratigraphy, you might get some you know, some kind of bridging, if you will, for a period of time where you're not getting that 100%, you're gonna get at least 50%.
So what's it do if you don't consolidate 100% to your liquefaction, just cranks it way up?
Yes, yeah.
Yeah.
You basically have a loose
Well,
well.
does
And
that,
what I didn't talk about here is this really sensitive time. You know, I talked more about long-term. You know, we have load restrictions, right, in the springtime. And we have load restrictions because the soils are really soft, right? And so like the farmer's loop, you know, where you have this silt especially,
Yeah.
that's really soft material. I didn't talk about that like in between time where you're even more susceptible, even soils that we might not consider totally like liquefiable by you know, really simple definitions, would potentially you know, cause us pretty big havoc as they're really young in their period of thaw. When we see that, I mean, I think a great analogy is load restrictions and weak soils as spring thaws out the active.
so you might really be under predicting the liquefaction potential.
Yes, yeah, at least in the short term.
Yeah, it could be like that.
Yeah,
But that
yeah.
short term.
Yeah, because now you're talking about the moisture has to go somewhere, right? And so, you know, you have, like in consolidation theory, you have one-way drainage and two-way drainage, right? Where if you have a clay that you're loading up and you give it two drainage paths to try to get the moisture out faster. Well, if you've got a frozen front on one side, and you only have one-way drainage and your consolidation takes twice as long.
Yeah, when you're frozen on top, it doesn't go anywhere.
Right? That's right.
It's just stuck.
Yeah. And you hope that's the case forever then, right?
Yeah, yeah.
So I'm kind of led to believe by your presentation that the main variable is the density of the soil. It sure seems like there's other variables that would apply to liquefaction that you can measure, things like clay content, grain size, friction angle, sort of things that would, so how do they?
Yeah, so this-
don't those variables not play into the liquefaction potential of the soil?
So that's a great comment, and this was kind of hidden in the weeds, if you will, of some of my commentary is that I had that N160 clean sand, and that CS, and they've accounted essentially for fines content there, up to roughly about 35%. Now, so this gets into the shift from classical liquefaction, like a geotech engineer, if you queried, you know, most geotechnical engineers, they'd say you need to have sand to have liquefaction, right? And then like say the, you know, 64 earthquake, we had, you know, this clay layer that had what we call cyclic softening, right? And so when you start talking about like cyclic softening versus liquefaction, now you're kind of like splitting hairs. And some of us like get up in the morning because we like to split those hairs. But you know, you have this kind of you know, liquefaction spectrum, right? Where, you know, if I asked you, do gravels liquefy? What would you say? Yes, no? They liquefy. And yeah, they liquefy and I'll show you how, right? You know, it takes big earthquake, it takes, you know, a really loose gravels. Now, the next question you can ask is, so what? Because one of the reasons why we don't have a really good database about liquefaction of gravels is that we don't know where they happen because we don't see a lot of settlement due to that liquefaction, like we do in sands and some others. So, but there's, you know, the liquefaction happens on the spectrum of soils. And so, you know, this is really focused on, say, a clean sand approach. But you can still see it in a variety of soils. And so
So this is the kind of liquefaction, like you go to the beach and you know, the waves come in, the waves go out, and you sit there at the high tide line and you stop the ground.
Yep.
Yeah. You can see the sand liquefy. I mean, it's
exactly
floating
right.
and such,
Yep. Yep. Your Mother Earth, yeah, imposing your load. So, yeah.
So ever getting to a soil definition where it won't hit your critical, at least in the liquefaction, it just isn't possible.
In what way?
Well, I don't know. I don't know, I'm just asking, because I would think you could type a soil and say it's gonna be safe, but there's just too many factors. Over the time we have in the next, well, I don't, but 50 years. To look at that, right?
Yeah,
Fascinating.
yeah, well,
Don't get me
and so
wrong,
what,
it's just-
my comment there
Because I
is
was
that-
thinking I could ask you, well, is there any void ratio where it's gonna be safe, but you've got too many factors now, and now he's bringing up other factors, so he just. Wow.
And I will say, we have some soils called thaw stable soils, right? And like
Okay,
you go
right.
back, say you do pile design, right? In pile design, we have a definition for, thaw stable, soils that we don't have to deal with if the soil thaws. And the whole idea, the whole concept behind the thaw stable soils is they don't have the moisture content to spread apart the particles. And they end up, you have densely packed or densely, dense particles, right? And so in a site, like there's another site in Fairbanks that I was working on where we definitely had thaw stable soils. It didn't matter how much ice you thawed out of there, got rid of. The soil was so packed together that you weren't going to have liquefaction, and you wouldn't have you wouldn't have a liquefaction problem.
Or settlement.
Yeah, or settlement.
I mean, has there been more work on settlement before you start talking about liquefaction? I mean,
Well, yeah, and that's another one. Yep, there's a whole host of issues with thawing permafrost.
I have a pile I put in Glen Allen in the 80s. I'm worried now.
Yeah,
Holding up the force main to the lagoon, yeah.
sure.
But I'm not gonna think about it.
Yeah, no, that's somebody else's
I mean-
problem now, right? Yeah, no, it's a really, this is it's a very exciting, but very serious, set of issues that we have, right?
Yeah.
Ahead of us, existing infrastructure especially.
So in the earthquake here in Anchorage, where some of the approaches failed to like Minnesota or wherever it was, were those gravels also involved in that?
Well, so Minnesota, I worked on the Minnesota,
Or-
off ramp.
Or even on which was new sewer, but go ahead, yeah.
Yes,
Okay. you
so,
did.
so that one, there was peat over top of sand, over top of much denser material, right? And, at the time, the peat was removed, but the sand was below groundwater level, right? And so the sand was left in place, and then they filled, and built the MSE wall over the fill, but they got rid of the peat, right? So peat that's good, right? But what happened in the 2018 earthquake is that zone of fine sand that was left in place liquefied, and that MSE wall translated and actually moved a little bit as
What is
well.
an MSC wall?
What's that?
MSC wall, what is it?
Mechanically stabilized earth wall. Those like panel walls that you see at some of the bridge abutments. They've got like the little plus signs or the little octagon hexagons. So they've got reinforcement in the back. So the whole thing moved, but it moved across this layer of soil that was left in place.
So you're saying the sand lost strength?
Yes. No.
Okay.
No.
Okay, it's all good.
It's all good. Yeah.
So I think the preferred method to build buildings is, in the normal slope oil field is to, the foundations are pile foundations. They drill a hole first. And then they put the pile in, and then they put a slurry in that freezes back, the slurry is a sand slurry.
Yep.
So, and then of course, they try to keep it frozen with thermal siphons. Would they be wise to use another soil? Another slurry mechanism?
Well, if you keep it frozen,
Let's just assume the thermal,
it's locked in.
gets to a point in the future where the thermal siphons are no longer effective because it's too warm outside all the time.
Be careful.
So then, would they be wise to use a different soil, different slurry than just sand in the slurry? It's just
Yeah.
water and sand basically. put in there.
They liquefy that slurry when you put it in place.
Right.
Like, it's vibrating
got
in place,
water in it.
it's
Yeah.
liquefiable as it goes in, that's how it works.
Right, it
So,
freezes.
yeah, if it were to thaw, you have a mess.
Yeah, no, I would say that, the thawed condition is probably, more severe for other reasons than, from an earthquake standpoint up on the North Slope, but yeah, that would be mine is thaw instability, is probably gonna be your bigger, issue.
Are people walking away from building sites now saying, no, We're not gonna do that now. We're getting to that point yet.
Well, I don't think so. I mean, I put a couple proposals in this week for places that people wanted to build on a questionable ground, and
Based on permafrost, thawing is what. I-
these were not permafrost sites, but yeah, you know, yeah, I don't know, I would guess no, I would guess that people are not.
Well, there's other pressures, but I.
But it does take years to develop, right? So I had a site that we worked on for, about 8 or 9 years and tried several different methods of design and construction before we finally found one that was cost effective, due to the conditions of the permafrost. And so they never walked away from the site, but, you know, it took a number of iterations, to get to something that was, cost effective.
So your practice insurance must be going up.
Luckily, at my level, I don't have to worry about that, with, you know, it's good for working for a big company. Nobody asks, nobody talks.
Nobody
about
asks
that. Yeah, yeah.
Do you think that or have you heard any rumblings of a code mechanism? Or future projections of this kind of thing?
No. I mean, there's, you know, so ASC has this, adaptive climate group that's looking at different things. But they haven't done a lot on the permafrost side, you know, they're worried more about storms and other things. Yeah, it's pretty quiet up here. I will say that, the Structures and Foundations Committee for, the Cold Regions, Engineering Division, for ASC is looking at this. I'm looking at putting together a kind of not, I wouldn't say guidance document, but some thoughts on the matter. Yeah, it's very timely. I
Yes.
Yeah.
Well, definitely, we're out of time,
All
so
right.
thanks, John, that was great. And, next week, or 2 weeks from now, I think there's another civil talk. These are the only 2 this semester, so the seminar series is running bi-weekly now, and we still have some openings in the spring, so if you're looking to that, we try to do at least half of them based on community input. We try to make at least half of them either civil or architect. And then the rest are, you know, electrical and make one. All right, thanks everyone for coming.
What's the code word?
Oh, code word is thawing. I think, right?
Yes, thawing.
Thawing. In my permafrost, it is thawing.
All lowercase.
All lowercase.
Thawing.
So
No.